Today we're going to be discussing measuring using different types of surveying equipment. And in this presentation, we're going to be in chapter 5 today. And we're going to be talking about the types of angles, measurements, and layouts, and then fill angles measurements. So in chapter 5, and then also on Wednesday, we'll be in chapter 14, covering parts of the different type of angles that you'll run into. The scope of this first section, we will be covering types of angles. It's covering how we look at angles and how it's important. So although distance measurements has been used since the beginning of time in layout, it has been long been recognized that angle measurements is also a method that could be used to locate points. And throughout history, it's always been that way. And sailing on the oceans and looking at the stars to figure out where the location is at, and looking at other means of determining where they are locating and height of things. So history shows that as mathematics developed and an understanding of angular relationships was formed, the layout tools of the time began to contain circles divided into angular measurements. As the telescope developed and was attached to these tools, the modern surveying instruments began to evolve. Each generation of angle measurements and measuring instruments has made measuring of angles easier with more accuracy and better precision. Now, angle measurements is just as important as distance measurements in the rapid location of points and on a construction site. Therefore, an understanding of the angles measured and the instrument used and applications to construction layout are presented in this chapter, in chapter 5, in the first section. So we're going to talk about different types of angles. We're going to start out with the horizontal angles. So the type of angles, the two types will be horizontal or vertical. In other words, horizontal, it's looking at one distance, then the vertical is going up and down. So yes, we take the grade, the ground, as a point, and we can go up to the height of a building and look at the angles. But also we can look at the angles laid out on the ground. So horizontal angles are measured in horizontal planes. When measuring the horizontal angle with a transit or deodolite or a total station, the angle is measured between 2 points that are sighted from the instrument, which is set up over a point representing the vertex of an angle. So we're going to briefly look at this, and this in the scope of is sighting into the first point, and the angle measurement circle is set at 0. In other words, when we're looking at a transit or another device to determine angles, we always have to find 0, start as a reference point. And then from that, once we determine that, we can go through all the other angles and have at least a reference point to start with. So, so again, that the first point, and when we're looking at horizontal angles, that first point, it is looking at a circle and setting it to 0. So the scope we are using is that then is turned to the second point, and the angle measured is read from the angle measurement circle on that device, on that transit. So it has a full scale around it. So the Horizontal angle measurement occurs on the angle measuring circle, which is independent of the vertical sighting. So in other words, it stays stationary as we move the scope around. So and this is with any type of scope that we are using. Doesn't matter if it's a transit, if it's some optical or digital control. This is explained more thoroughly and later in this as we go along in this chapter, but as we look at it, we're going to talk about different type of angles. So again, there's vertical and there's horizontal angles. When it comes to horizontal angles, we can look at both either internal angles or deflection angles. So internal angles are horizontal angles that are measured from an instrument that is set up on a point that is located between 2 points. Interior angles are often measured to determine the angle of a closed geometric figure. And you can find that on page 5-3. Deflection angles are angles that are horizontal angles that are measured from a prolongated and a preceding line. So it's not a closed fixture, but it's open. So it goes in multiple different directions. So it might go north, they might turn northwest, and it might go another direction, go back and forth, but it's what we call deflection angles. So therefore, the instrument is set up on the end of a line and is sighted back into that line. The scope is then plunged in the opposite direction and the line is extended. If the angle is turned off of this extended line, it is called a deflection angle. This type of angle is used quite often in route construction applications where angles off the straight line are measured. And again, it's going in multiple different directions. So in other words, it has a common point where it starts at, and then once it ends, it will follow in a different angle from that second point. So the third point would take that point, go to the fourth point, and so forth. They just keep going back and forth. So it's deflecting off each other. And so we call that deflection angles. So this type of angle is typically very small and require great care because of the tendency to extend lines well beyond the limits of the instrument, which will be causing error in the measurements or the layout of the angle. Now, the next one is the vertical angle. So vertical angles are measured in a vertical plane. That is, when an instrument is set up and leveled, the angle is measured using the vertical circle of the instrument. When measuring a vertical angle with a transit, a theodolite, or a total station, the angle is from the 0 point of the circle to where the horizontal crosshairs intersect the point where the vertical angle is desired. The method of vertical angle measurements will vary with the type of instrument used. With the transit, the vertical angle is 0 when the scope is horizontal, and the angle are positive if the horizontal, or negative if it's below. In other words, the crosshairs, we're looking at the horizontal line. With theodolites, the total stations, 0 is typically located at the zenith of the instrument, and all angles are positive values. I will have a YouTube video embedded into this so you'll be able to view what these angles look like for both horizontal and vertical.
idea to submission, empower students to do their best work.
Yes.
Hi, I have a quick question.
Yes.
Up until what time are the kids here?
It's about 3 o'clock.
3? Okay.
Yeah.
All right.
So you can start wrapping things up before that. So if there are any things they need to pick up and things like that, they can do it.
Okay.
But yeah.
Yeah, we're wrapping up with lunch right now. There's
Oh,
just a
okay.
few kids that are finishing up. It's just because the little ones are starting to get restless, so
Oh yeah, yeah.
I think I'm gonna start the activity with the younger ones, and then as they start finishing up, like they
Oh
can
yeah,
clean
yeah,
up
yeah.
and then just come and join.
Yeah, it might be a good idea that they can probably break them in groups.
Mhm.
There might be some more people showing up here to help with the enrichment, so you can certainly let them know what they can do. But I would say keep the kids divided up what they're going to do, like the older kids.
Yeah.
But you got it, you got it.
Yeah.
So they you may be working with something with the young kids, and the other ones might be just kicking the ball around.
Yeah. Yeah. I figured because I know that there's some boys there that they're not gonna want to put beads on a string, you
Yeah.
know, and tie them to a stick. So,
Yeah.
and that's fair.
Yeah.
All right. Sounds
Okay.
good. Thank you.
Oh man, there's some good stuff.
Hello, this is Ryan with Ivy Tech, and today we're going to show you how to measure an interior angle of a traverse using a digital theodolite. So currently I have a CS Turner EC10 digital theodolite. We have the corners of a real traverse mark, so it's steering wheel
Thank you.
Okay.
Yeah, you can leave it. There are two kinds of angles that are used in the field. Angles are either measured or is laid out. Of course, measuring is actually using a scope to, at a fixed point, and finding out the distance between and angles between the 2 points, or it's a layout where you're actually setting your points. So angle measurements is when it is desired to determine the value of an angle between two lines. The angle is measured. In this process, the instrument is set up at the point where the angle is needed, and the instrument is sighted into the adjacent points with the horizontal circle of the instrument and recording this angular value in degrees, of course. So the angle layout is when you want to locate a point on the job site and an angle needed to turn to locate it. So you are performing, in that case, the angle layout. In this process, you turn the angle and measure the distance to lay out a point. The instrument is set up on the required control point, and a sight is taken to another control point. The instrument is turned to the angle and the telescope is sighted toward the needed point. So next we're going to be talking about the field angle measured in the field, measuring. So in this process of turning angles, procedures such as direct and reverse closing the horizontal, transverse angles, the layout are performed. Proper performance of these methods is necessary to eliminate error and mistakes in the angle measurement. So first we're going to talk about direct measurements. So direct procedure is the simplest method of angle measurement and is performed most often by individuals and technicians in the field. In many instances, turning a simple angle is all that is needed, or is the standard practice for certain field situations. For instance, when performing radio layouts, most angles are turned just one time to the point that is been measured and been established. Now, when it comes to reverse. So when it comes to reverse, we're doing both. This process is doubling the angles. It is used to eliminate instrument errors and increase the precision of the angle turned. This involves measuring or laying out an angle with the instrument in this direct position, and then again in the reversed position, so that the angle between points is measured twice. Generally, direct is when the vertical circle is on the left as you are sighting through the telescope, and the reverse is when the vertical circle is on the right as you sight through the telescope. So referring to the owner's manual, because every device out there you're going to be using might have some different idiosyncrasies because of the manufacturer, but they all want to work the same, but we need to be able to look at it. So for greater precision, turn more than one direct and more than one reverse. On a critical control where angles must be absolutely correct, turn angles 2 directs and 2 reverse, and 5 direct and 5 reverse, even 10 direct and 10 reverse to obtain the best estimate of the true value possible. In other words, if you want to have to be exact, it's not just one time you say, well, I'm just good, I've been doing this for years, but you must be accurately measuring it by checking and double checking and triple checking and continue to checking. So that's extremely important that we do that, not just taking it for granted. So closing the horizon. So this method is used as a simple check to ensure that the angles about a point add up to 360 degrees. For example, an instrument set up over any point, all angles at that point are turned and the horizontal is closed. When the angles about the horizontal are added, they should meet the predetermined closure. If they do not close within acceptable amounts, the angles are discarded and turned again until the results meet the required standard. In other words, we're taking multiple measurements. We starting at one point, taking these measurements, and now we verify it by going through. If they add up to 360 degrees or something extremely close to that, then we can say that it is accurate. There's no major errors. So we're going to look at field angles measured going into transverse angles and layouts. So when it comes to transverse angles, is when the relative location of a series of control points. In other words, more than one point in different spots. In other words, you're sitting back and you're measuring these different angles. So when the relative location of a series of control points to each other is needed, transverse angles are measured. This involves measuring all the angles of the transverse and determine if the transverse is a closed geometric figure. Transverse can be either closed or open. A closed meaning like it's a closed box or an octagon or whatever you measuring, and it adds up to the correct number of degrees. And so where you start at will be its ending point also. So that is a closed transverse. And so when measuring transverse angles, it is common to practice to turn the angles at least one direction, one is direct, and then of course come back reverse. And more likely two direct and two reverse. Even for greater precision and to obtain a better estimate of the true value of the angles at the control points. So in other words, nothing changes. You check yourself, you verify. So when it comes to laying out, so layout is once the control point has been established and direct and reverse transverse angles have been measured, site activities will turn to layout. In other words, once we found those marks, then we start to lay out physical points, putting stakes in the ground, laying out where things need to go. So angles will be obtained from the plane or from calculations to lay out the construction points on the site. Although most points will be laid out with a single direct angle, it is good practice to use the direct and reverse procedures for layout of important points, such as the center of a bridge, abatement, or an elevator shaft on a building, or a stairwell, something that must be in an exact location. So again, multiple measurements is necessary. Okay, we're going to go into instruments right now. We're going to look at the scope of instruments and the different types of instruments that we will come across. So when an angle need to be determined or laid out in the field, or angle measurement instrument is called either a transit, a theodolite, or a total station. And it is used in this case. Now, of course, starting with the transit is the most simplest one we can find. The theodolite is the next step up from that. Now, the total station is the new kid on the block. It's been around for a while, but it's basically a computer system. And it's more accurate, and it not only just angles, it can measure distance too and do calculations for you, save you a lot of time. So again, the instruments all do essentially the same thing. They measure angles. Their differences are described by the changes in the instrument development and technology. The transit was the original angle measurement instrument and was a highly sophisticated instrument when it was developed. It has since been refined by the optical theodolite first, and then now by the total station. So the field engineer must have an excellent understanding of the angle turning instruments been used, as well as the process of measuring angles whenever possible. So control will not close. So if we don't do it, if we don't take accurate readings or use the instrument the way it was designed, when we are measuring things, or let's say we're doing a transverse and they don't add up, so the close the control will not close. The structure will not fit together. Accurate layouts by coordinates will be impossible. So a good field engineer must understand the importance and becoming an excellent operator of angle turning instruments. This section will cover an overview of these various types. However, it's not going to go over the very specifics of any particular manufacturer, because they all work basically the same way, but of course we couldn't cover everything in this chapter. But we will go into the total station in chapter 6, where we cover a little bit more information about these things. So let's look at the overview of this section. So again, there are many types of angle measuring instruments in use in the construction site today. They include the transit, the theodolites, the digital theodolites, and the total stations. Even though the name are different, they look different, and they operate a slightly different, they all are used in the same purpose: angle measuring and angles layouts. So again, as we look at this, there's many parts of this here. We see that it's designed to be accurate. They read angles in the same direction as they turn. They can read horizontal circle, but they read the vernier where the lines match exactly, and that is the scale. That's the scale on the transit, or the scope. As you turn it, they get the scale on it. So again, we can add all these up. We can look at them. We can know exactly how they operate. But when it comes to the transit, it's like I said at the beginning, this is a picture of a transit with the. And you could tell this is an older style. Today, it's probably made out of plastic. You can still buy a more expensive one, but the purpose of it is still operate the same. So again, as we look at these, taking measurements, basically you're collecting information for two reasons: to either find points or to lay out points. So establishing points and laying out points. Those are the two main things you will end up doing. So let's talk about the transit first before we go any further. In the transit, basically, it was developed to its present form during the 1800s. In other words, in the 1800s, when it came out, it was a precise instrument. And know where it came from? Actually, from the nautical industry, where they use a sextant. A sextant was a device they hold in their hands, and they find some point, and they will look at the moon or the sun. They had a filter if they're going to look at the sun, but they was able to find out exactly where they was located by finding a fixed point. And the fixed point was a star. It was either the moon. It was something they can use. So during the daytime, it was the sun. So they had to know exactly what time it was. So they have to have a timepiece, an accurate timepiece. But anyway, that's how it all started in the 1800s for laying out the ground. Before that, it was measurements and using other type of devices to do it. So a good, solid, and reliable instrument, the transit, is still used in many construction sites today. However, optical theodolites and technology and the new digital electronic technology have passed it by. The major companies who manufacture transit have dropped them from their product line. Many of them have, but the thing is that they went to other types of surveying equipment. So the transit major contributions to the field of engineering today is that it is a good tool for learning the fundamentals of angle measurements. It is its parts are exposed, making it easier to see what is going on during the manipulation of the clamps during the angle measurement process. By understanding the transit, the field engineer can easily move on to any other type of angle measuring equipment. So although there are a number of different between transits and theodolites, and the major difference between them is the method of reading the scales. The typical transit has a metal horizontal circle which is marked from 0 to 360 degrees and is graduated to the nearest 20 or 30 minutes of an arc. A description of the typical theodolite is presented later in this section. So the vernier is then used to obtain more precise readings to the nearest 1 minute or even the 20 seconds of an arc. So here's really quick to look at a compass, and we're looking at the vernier on it, and it's graduated. It's graduated in minutes and seconds. And again, it's to get more precise measurements. So of course it's degrees. There's minutes after that, which is smaller, and within the minutes will be seconds. And we can graduate it all the way down to something very precise to get accurate readings. So again, when it comes to the transit is the one that's been around forever. So let's talk about the optical. Well, these are the basic ones, and this is a picture of the theodolite. Of course, there's the optical one and there's the digital one. So when it comes to the different ones that we see, that we're going to cover each one of these separately. So the transit, I gave you most of the information about it and how it's set up and what is used. So this is definitely a transit. And again, you can't see it very well, but there is a scale on it, and where you can see the degrees as you find your points. So again, basically reading the angles clockwise angles. So reading a clockwise angles on a transit vernier, of course the vernier is the scale on it. So read the angle in the same direction it was turned. Observe the direction of the angle was turned. Everything is to be read in that same direction. So in other words, when you start one direction, continue moving in that direction. If the angle was turned clockwise, the vernier and the circle must be read clockwise. And usually you would do that because the scale, if you look at it, it's actually go counterclockwise. So you will move it toward the right. You twist it around that direction. So if you go clockwise, continue clockwise. If you're going counterclockwise, continue that way. So it depends on the scale you are using. Again, always check your tool you're using because it can be the other direction. So the optical theodolite, it's a term that was originally applied in Europe to instruments similar to the transit. However, as the instrument technology progressed, the term theodolite became synonymous with a style of instrument that was enclosed, used a magnified optical system to read the angles. And it had a detachable tribrid with a optical plummet. And it was used, of course, a 3-screw leveling system like we find with a lot of transits, and was now more precise than the transit. So the better optical theodolites have been, it's kind of funny, a delicate workhorse since they have been introduced. That is, if they are properly cared for, they seem as though they would last forever because of their excellent construction and the quality of the materials used. However, they must be handled gently and carefully. A typical optical theodolite may have as many as 20 prisms or lenses as part of the optical angle reading system. With a sharp bump, these can get out of alignment and may render the instrument unusable. So again, we must take care of these things. Must take care of it, not dropping them around, not kicking them around, keeping them in the case. So as with any surveying equipment, the theodolite cannot be exposed to inclement weather. It's raining, snowing outdoors. The work shouldn't be not done. It should not be done at that time. So again, just like any other type of tool that we are using that is precision instruments, that it must be taken care of. The repeating theodolites contains the same upper and lower clamp systems as the transit. However, the reading of the angle is different because of the optical reading capabilities. This instrument also has a glass circle, but it does not have a scale, as it has a micrometer used to precise the reading the angles. The operator of the instrument turns the angle, and then the user then uses the micrometer to align the degree index, making these index marks. The micrometer is used to optically align the degree index marks, and the reading of the degree window and the micrometer window are added together to attain the angle. So we look at both of these. As long as everything is balanced and leveled out, we can take these measurements and be able to know exactly what the numbers are. So the scale reading theodolites are excellent instruments, but just like the transit, they are also been surpassed by the electronic technology of modern instruments. So operationally, they have a locking lever that is used in conjunction with a horizontal motion of the to manipulate the circle in the angle turning process and procedures. This is a very rapid system in turning angles and is an excellent construction site instrument. The typical scale reading theodolite is a glass circle with a simple scale that is used to read it. So simply read the degree that shows up on the window and observe where the degree index mark intersects the scale. Both the horizontal circle and the vertical are generally observed at the same time. See the illustrations for the example. We could turn to page 5-9 to get an idea of the horizontal angles and the vertical angles. So it just makes it a lot easier to get the those measurements. Now the digital theodolite, that's another one we're going to talk about, we're going to get into. So in this here, it's a lot simpler. It's just a digital readout. So the digital electronics has recently entered the arena of surveying equipment. Angles are no longer read on a circle or with a micrometer. They are displayed on a screen. The metal or optical circle of the pads have been replaced with electronic sensors that determine the angle quickly and precisely. From a distance, the digital theodolite looks like an optical theodolite in size and overall shape. Actually, the manufacturers did build the original digital instrument on the same structure used for the optical theodolites. The telescope, the clamping system, the tribric, and the optical plummet are the same. Only the angle measuring and the reading system is different. Because it is electronically based, the digital theodolite is like other electronic equipment. It either works or it doesn't work. If a circuit goes out, the instrument is useless. If the battery is in charge, the instrument is useless. However, it is a great instrument when it is working. The advantage to the contractor is that it is typically less expensive than the optical theodolite. Isn't that amazing? But here's the reason why: all the prisms that's inside of the optical. And so again, the electronics brings the cost down. So the digital theodolites are easier to read as reading the display on a calculator. The angle reading is presented in degrees, minutes, and seconds format. The hardest part of the field engineer is to transfer the angle from the display to the field book correctly. And that's the only thing. So it makes your job a lot easier and faster. Let's talk about the total station. And a total station, of course, you can see a lot more to it. So it is the electronic total station is the ultimate of survey and measuring instruments. It is a combination digital theodolite and electronic distance measuring instrument, and we call it the EDMI, and also known as the EDM, which allows the user to measure distance and angles electronically, calculated coordinates of points, and attach an electronic field book to collect and record the data. The electronic total station does it all for the field engineer, operates as operating it. So in other words, that's why we call it the total station, because it does everything. So what total stations are capable of doing is simply phenomenal in comparison to the way field engineers have to measure just a few years ago. Complex projects can now be calculated on a computer in the office, and the data uploaded to the data collector. The data collector is then taken to the field and connected to the total station, where hundreds of points can be rapidly established. So reading an angle on the total station is similar to the digital theodolite reading system. The only difference is that they may be more data and options displayed on the screen because of the distance measuring feature. Be careful when reading the display that extraneous information isn't recorded instead of the actual angle. A sample is shown in the illustration and on page 510. So if you look at page 510, you can see the picture right there in the middle. So we're going to keep on looking at instruments and understanding what they're going through. Again, there's many different components that you find when you're out there, but on page 5:15, getting into um, uh, different practices of using a total station. So again, when measuring horizontal angles is a simple mechanical or electronic uh, mechanical procedure that can be readily can be learned by reading and studying in the owner's manual of the equipment. So no matter if you have a simple transit or a optical or digital theodolite or a total station, you should always be familiar with that device before using it. Just don't take it for granted because, again, you can throw information off. So, again, look and make sure everything is working correctly. Again, some of the basic practices that we look at, reading the owner's manual, going through it, making sure you're setting up things correctly, putting the tripod in the ground securely, making sure it's balanced, make sure it's level, making sure you're setting up over a point, and that you're using, if it's a transit, that you're using a plumb bob to balance and make sure that you're finding that point, that everything is exactly the way you want it. Now, again, when you're focusing, that's another thing that we must look at. Focusing with um, your equipment to know what you are setting for and looking through, making sure things are brought into focus. Not only just the object, but the crosshairs too. They both must be seen clearly. So some devices you can actually adjust the crosshairs to set it in to make sure it's crisp in the right place. And also focusing on the object that you're focusing on. So focus is, again, it's important that you're adjusting, not over tightening things, not under tightening, that things are secure, and that the instrument is performing correctly. So focusing again, so when you focus on the object, focusing on the object for each shot is necessary. In other words, you just make one point, then you change it, you refocus it again. Since the distance of each shot will be more than likely be different. Even if you're doing a reverse from and you're just checking it, you could be off. So yes, making sure that your points are correct, and that's an indication that you may be off. When if you're doing a reverse and you find out that it's not correct, you may need to reposition. So when focusing on the object, select a part that can be seen clearly and turn the focus knob until you can see sharp. So look at several parts of the object, of the objective for fine details and adjust the focus knob until the absolute best clarity. Now, when you're focusing the crosshairs, often throughout the day will be necessary because the human eye tires and as the day progresses and and the ability to focus changes. Again, if you're staring at something long enough, your eyes will have a tendency to adjust to that sight, and so you might need to take a break sometime. Or of course, we need to refocus so you will be able to see what you're looking at. So again, when focusing on the crosshairs, look at a light color object like a white house or a cloud in the sky or a piece of paper. So adjust the eyepiece on the instrument to make the crosshair as dark as possible. You can't do it very well if you're looking at something already kind of dark, like you're looking at greenery. Um, it's You can probably do it, but again, against a white background would make it a lot easier. So again, having good targets. Now, one of the things you can use in the field is these targets that you can use, that you can put it on your scale. You can put it out there and be able to focus on, where you get these sharp lines where you can actually dial it in. And so again, your bullseye, your crosshairs must be seen clearly, very clear. So leveling the instrument, focusing on the object and the crosshairs. And one thing that you need to do, if you see double lines or there's issues, we probably need to adjust and get things tighter. So again, these are a lot of hints that you can use to be able to help you in your angle measurements. So looking at the horizon angles and measurements, some of the things we're looking for is that making sure the equipment that's installed correctly, that is level, that is balanced, that the scale on it is set, but also checking when you're taking readings that you're taking multiple points to verify that things are correct. And one of the things when we call close the horizon, where we're taking measurements and then it should always come back to 360 degrees. It should add up if you're taking the different angles. So when you're measuring, just make sure that you check your equipment and you check your work. Both of those will help keep errors down and certainly eliminate mistakes. So verification and everything. So closed horizon is to confirm that the angles add up to 360 degrees. If turning several angles after the final angle back to the original back sight as a check of 360 degrees. So if you go back and go to the point where you first started at, it's going through, it should line up at 0. So in other words, the scale shouldn't change. It should be dead on 0 or 360. It should add up every time. I got a video here that goes through to finding the to close the horizon. On page 518, it goes over the basics of turning an angle. So in other words, once you set your point, set up and level over the point. In other words, you know where you're starting at. You define that point. You made a mark there. You verify, make sure everything is plumb. So now you start to loosen the clamps. Next, you set and hold 0. In other words, bring it to 0. You got that point where you're starting at, set it to 0. Sight and lock into the back sight. The back sight is where you are measuring to. Okay, and now the next thing is that you're going to release 0 and release the horizontal motion clamp. So you're going to turn, you're going to sight, and you're going to lock into your foresight. Read the angle, record in the field book. And so again, once you record it, that become a number. You can also, like I say, you can verify it too, unless you're just taking one point. It all depends how critical it needs to be. So measuring transverse angles, and so we can, again, procedures for, we kind of went over it already, looking at the procedures for doing direct and reverse angles, just verifying it. Transverse angles too, basically you just move through everything as you're doing it. So measuring transverse angles. So the transverse is the fundamental tool of surveying, because you're not going to stay in one spot. You're going to go move around the property. By knowing the angles and distances about a transverse, again, the architect may have laid everything out already. Now you may have to come back to verify the set points to do your layout. So the position of the work can be determined to see if the measurements meet established standards. If the work is good, the angles and distance can be used to calculate coordinates for each transverse point. This information is used to determine mapping work and to establish grid systems on large construction projects, among many of other things. Now, again, the grid work, like if it's a very large warehouse, they would actually, because the warehouse is so large, they would put a grid in the prints to know where every beam was going to go, and they give it a special number so you know where it needs to be set. But other things also. So all this is necessary when we take in measurements, especially the transverse, looking at the horizontal, and of course the measured distance of each one of these. So standard practices, and we covered a lot of these already, but again, communication is big. We must be able to communicate, confirming your backsite. And let me just talk about backsite. Backsite is the single greatest mistake in angle layout, is using the wrong backsite to measure the angle from. When performing layout on a project with numerous control points, it could be very easy to mistake one point for another if both are in the same proximity. Even if the points have been marked clearly, it is possible for someone to inadvertently to get on the wrong point and give a line to a backsite, or perhaps numerous targets have been established around the site, and it could be easily to sight into the wrong target. Always perform an additional check to ensure that the correct point is used as a backsite for the angle to be turned. So again, if we go look at page 526, 527, it goes through a lot of those. Let me see if I turn my book, and it goes through procedures and steps how to go through each one of these sites. Again, a vertical or zenith angles. And you're going to find that on page, it goes, well, start with the procedures on page 25. But if you go to page 528, we can see the vertical or zenith angles. Matter of fact, if you see the diagram on page 528, they give you the point where you're starting your measurement from, and then looking at your angle positions to find out exactly what those vertical rises are. So the zenith is your starting point. Again, so the scope of this part is really just looking at these different components. So the zenith is basically, or is, like I said, that starting point. But occasionally, the field engineer need to measure vertical, or we call the zenith angles, as part of the establish of a control point, or to lay out of a distance, or to determine elevations. Accurate vertical angles are necessary to precise calculated horizontal distances when using total stations. As many persons regularly use trig leveling to determine the transfer elevations onto a construction site. Again, all angles measuring instruments are different. So the procedure outlined in what we're going to talk about will not apply to on all cases. But of course, you can get the basic fundamentals that we'll talk about in this section here. So we can look at the transit, the theodolites, and of course the total station and how it works. So when it comes to a transit, the transit vertical angle are measured off the horizontal. horizon. Again, looking at the horizon. Above the horizon and is positive or it is negative. Okay, of course, going up is positive, going down is negative. The theolites, the vertical angles, are measured off the zenith point. In other words, the height where you're looking, where you're sighting it through. And the standard practice is the same as the horizontal angles and measurements as we look at that. So again, the standard practice is, even though the vertical angles are measured in a vertical plane, many of the standard practices of instruments used and horizontal angle measurement still applies. These include communicating, sight carefully, and read the angle correctly. Also, to other points that is necessary, make sure the instrument is level. If it's off level, your angle is going to be off. Sight the horizontal crosshairs. And sight exactly on the target, what you're looking for. Not slightly off, but exactly on it. And we're about ready to close out, but looking at the calculations and looking at how we see things. And so as we look at the direct calculations and measuring things, of course, like I say, we looked at the starting point, looking at the horizontal, looking at the zenith, but knowing how we measure. Okay, bearings, again, looking at the two different ones. Bearings is basically looking at the degrees of the ground and where it's located, but the other is looking at degrees. In other words, degrees of north, south, east, and west. But of course, all scales will look basically the same way. It's 360 points between each one of these. So as we look at our bearings, we look at our measurements in degrees, we can be able to find precise points and locate them and be able to lay them out.